So welcome you to today's lecture. If you have any doubts from your previous lectures, you may ask or clarify those doubts. Any doubts from your earlier lectures? Okay, if there are no doubts from your side, let me just start. Today's lecture. Okay, so what we were doing last time is we're trying to start with the concept of a minimal sufficient statistic. What we discussed was that sufficient statistics helps us in reducing the data without losing any information that is contained in the data. So in principle, there can be infinitely many sufficient statistics because all would reduce the data without losing the information. The idea is, among all these sufficient statistics, which one to choose? Then certainly the choice is the one which gives me the maximum reduction in the data. So that leads to the concept of a minimal sufficiency. What we'll discuss over here. Now, to understand the concept of reduction in data, simplest example is, let us look at two statistics. We have seen that each statistics induces a partition, right? So let us look at the statistic, the whole sample x1, x2, xn. This is one statistic. And another statistic is x bar. Which gives you more reduction among these two? X bar gives more reduction, right? Because it is only one dimensional. More reduction in data. And that is happening because x bar can be calculated from x1, x2, xn, but x1, x2, xn cannot be calculated from x bar. So it is reduction in that sense. So that means I should look for a sufficient statistic. So x bar is a function of, so if x1, x2, xn was also sufficient and x bar was also sufficient, I would have preferred x bar because both are sufficient. They contain the same amount of information. But x bar gives me more reduction in data because x bar is a function of x1, x2, xn. So if you have a two statistics, T1 and T2, and T1 is a function of T2, then certainly you will prefer T1 because given the knowledge of T2, you can determine T1, but not otherwise, as is happening over here among x1, x2, xn, and x bar, if both were sufficient, I would have preferred x bar because x bar is a function of x1, x2, xn. That means given x1, x2, xn, you can calculate x bar. It is reducing a data, so because x1, x2, xn, a lot of other information. X bar says, no, I just need their sum divided by n. So x bar is a function of x1, x2, xn. And if both are sufficient, certainly I'll prefer x bar. So in general, if T1 and T2 are sufficient, both are sufficient, so they fulfill our criteria that they reduce the data and they contain the same amount of information. And T1 is a function of T2, is a function of T2. If this is happening, what you should do? Which one should you prefer? Anyone? T1 and T2 both are sufficient, but T1 is a function of T2. So which one would you prefer? T1 is a function of
T2.
T2. It was happening over here because X bar was a function of X1, X2, Xn. So X bar was giving a more reduction in data. So here T1 is a function of T2. The T1 will give you a more reduction in the data. So I would prefer T1. T1 is preferred. That means you should search for a statistic. You should search for a sufficient statistic, which is a function of any other sufficient statistic. That would be the most preferable sufficient statistic because it is a function of any other sufficient statistic. So it gives you the maximum reduction in the data among all sufficient statistics. Now we call such a statistic to be minimal sufficient. So a statistic Tx is said to be minimal sufficient if it is a function of every other sufficient statistic. That is, Tx is minimal sufficient if, first of all, Tx should be sufficient. And if you look at any other sufficient statistic, let us say Ux, Tx should be a function of, that is a definition of a sufficient statistic. So what is a minimal sufficient statistic? It is a sufficient statistic which is a function of any other sufficient statistic. Now let's look at this thing in terms of a partition. Suppose Ux is a function of Tx. Now when you say that f is a function of x, what does that mean? That means it is a map. The only condition of a function is same point cannot go to the two different points. If x and y are same, then fx should be same as fy. So x is a function of x if and only if x equal to y implies fx equal to fy. Why? Because the same point x cannot go to two different points. So if x is same as y, fx has to be same as fy. You cannot have this kind of a situation. This is the same point and it is going to two different points. This is not a function. Right? Because the same point cannot go to different. That violates the definition of a definition. Function. So function ensures that if x is same as y, then fx should be same as fy. So when I say that ux is a function of tx, what does that mean? That means if tx is same as ty, then ux should be same as uy. That is what exactly it means. Same, it follows from here, this definition, because u is a function of tx. So if tx is same as ty, then ux would be same as uy. Same point going to. So it is like this. U is a function of t. So t here, and this is also going over here. Sample space is a function u, and from u, you may have this over here. But u is a function of t, then because this is coming over here, so this should go to the, this should go to the same, right? So that is, these points are same, that should be the same. What it means is tx is same as ty, then ux should be same as uy. So, so you cannot have a situation where ux and uy are different, but they go to the same. Ux and uy are same, but they go to the different. Just a simple definition of a function. So let us look at the partition induced by statistic t. So let us look at the range of statistic t, which is t of chi, which is collection of all those tx, says that x belongs. U is the range of the function u, which is u of chi, which is u of x, collection of all those u of x, says that x belongs to. Let us look at the partition induced by the two statistics. So a typical partition set would be BU, where U is the value assumed by the statistic U. And then I look at all those X which map U to U. Each of these give me a partition set. Similarly, CT, T belonging to tau, is a collection of partition sets induced by T. So it is collection of all those X belonging to T, says that Tx equal to T. We look at different values of T, look at the what are the X's which are mapped to this value of T. Now, this we have seen earlier also, how to determine these partition sets. So that BU, U belonging to script U, and CT, T belonging to T are two partitions of time. Then clearly U is a function of T. That means for every U belonging to U, DU is same as this. Why? Because let us look at this condition. U is a function of T. So that means U depends on T. X to chi is going like this. And since U is a function of this point may go to this point can also be achieved by over here. Let us look at this particular point over. This point is a union of what points in T? It is union of these 2 points in T. So that means a single point here may correspond to more than 1 point over here. So that way, if I look at the partition set BU, it will be the union of partition sets of T. Right? For example, if it was only singleton, what was the points over here? It was this point as well as this point are going to. So BU is union of T belonging to T naught. So if T is a function of U. There's a partition associated with a minimal sufficient statistic because T would be a function of U is there's a spelling error, coarsest possible partition for a sufficient statistic. So each partition here would be a union of partitions in the set T. So it would be like this. So this is the Tx partition of T induced by this. Ux is psi of Tx. So each of these points go to the same point. Each of these goes to the same point. So sufficient, minimal sufficient statistic achieves the greatest possible reduction of the data. Let us look at now an example. Suppose I have a random sample from normal theta sigma naught square. Theta is unknown and sigma naught is known. Then you know that your joint PDF can be written this. It can also be written like this. I add x bar and subtract x bar. But note that by factorization theorem, if I had faced, I would have consumed this part because sigma naught square is known. I would have consumed all this part to Hx. Because this is this into e to power minus 1 by 2 sigma naught square x bar minus. But choice is mine. I could have, I could not have. Factorization theorem gives me that liberty. So if I apply the factorization theorem, it tells me x bar is also sufficient. Because in that case, I consume this with Fx, and I take this as psi of Tx theta, which is psi of x bar. I could, factorization theorem also gives me a freedom not to subsume this into Hx, keep it with psi of summation xi minus x bar whole square x bar comma theta. I could have taken that also. So by factorization theorem, x bar is sufficient as well as this is sufficient. X bar and summation xi minus x bar whole square. In fact, by factorization theorem, the whole sample is also sufficient. In fact, T3x whole sample is also sufficient. Because then I can write down this as a function of psi theta of x1, x2, xn. So that is also sufficient. Thus T1 and T2 contain the same amount of information about theta. However, T1 gives greater reduction of data than T2. Now note that T1 is a function of T2 because once you know T2, you can get T1 by just picking up the first coordinate. So note that T1 is a function of T2. And how do you do that? What is the function? R of T2, which has two coordinates, T21, T2. It says you can get T1 only through the first coordinate, which is T21, which is T1. So here the additional information about the value S square, which is this quantity, does not add to our knowledge of theta, since sigma naught square is known. Of course, when sigma naught square is known, then actually I should write down. Of course, when sigma naught square is unknown, let me correct this. Of course, when sigma naught square is unknown, then T was x, which is only x bar, is not sufficient. And in fact, sufficient, we'll see that because by factorization theorem, we cannot conclude that x bar is sufficient. Because sigma naught square is also unknown, then I cannot separate it out from an unknown parameter. In that case, x bar and summation xi minus x bar whole square will be sufficient. And we'll see that, in fact, when sigma naught square is unknown, T1x is not sufficient. And T2x is equal to x bar s square contains more information about theta sigma square than T1x. Now the question is how to find minimal sufficient statistic. So the next theorem tells me a way to find a minimal sufficient statistic. So suppose X belongs to the parametric family of theta, which is f theta, theta belonging to theta. And let f theta be the joint PDF or EMF corresponding to f theta. Suppose that there is a statistic Tx such that for any two sample points x and y, SO f theta x upon f theta y is independent of theta. That means it is constant as a function of theta, if and only if Tx equal to T1. If there is a statistics T such that for any two sample points x and y, f theta x upon f theta y is independent of theta, if and only if Tx equal to Ty, then Tx is minimal sufficient for theta. So how do you find a minimal sufficient statistic? You look at for any two arbitrary sample points, you look at f theta x upon f theta y. If this is independent of theta, if and only if Tx equal to Ty, then you say that T is minimal sufficient. The proof is not difficult. For simplicity, let us assume that f theta is positive on the sample space. Otherwise, you can define this as a sample space. Now I define tau to be the range of the statistic T. AT as the partition induced by this statistic. So ATT belonging to T is the partition induced by the statistic T. So what I do is for any T in the range of AT, choose and fix an element xt in AT, because for every T there is a pre-image of this point T. So I choose pre-image as xt. So for every T belonging to, I choose one pre-image xt. Then xt depends only on T for a given Tx, for a given statistic. Because it only depends on T. You are looking at the range. What is the point in the range? You are looking at its pre-image, xt. Because xt is not unique because more than one point may correspond to the same T. Moreover, for each x belonging to chi, x and Tx are in the same AT. Why? Because Tx, T of x takes value Tx. And what is the T of x Tx? So if, for example, if Tx was T, what would be Tx? Tx would be T. And how I have chosen xt? I have chosen xt says that its image is Tx. So T of xTx is also T. So T of x would be same as T of. Because if Tx is same as T, then you know that Tx is T. But how I have chosen xt? I have chosen an xt belonging to AT. How it is chosen? Such that T of x of Tx is basically this point T. It is like this. So suppose a point was x, this point over here is a sample space. This is tau, which is now there are 2 points. Let us look at this like this. And this is x. This is, let us say, T. So Tx is same as T. And there is another point, which is x of T, which I have chosen. Because for every T belonging to 2, I choose a one element xt in AT. Because this would be a point in AT because both are going to AT. So if Tx is T, then x, so this would be xtx, then Tx would be same as Txtx. Both are going to T. So consequently, we know that f theta x upon f theta y is independent of theta if and only if Tx is same as Ty. So that means independent of theta implies Tx equal to Ty, and Tx equal to Ty implies that f theta x is same as f theta x upon f theta y is independent of theta. Does not depend on theta. Now, since Tx and T of xtx are same, so that means f theta x upon f theta xtx would be independent of theta. So that means it will be a sum function which will not depend on theta. I call that as hx. So that means f theta x would be same as f theta of x of tx into hx for some h. What does that mean? By factorization theorem, this means Tx is sufficient. Now I prove it is a minimal sufficient statistic. Once I have shown that it is a sufficient statistic, to show that it is minimal sufficient statistic, I have to show that it is a function of any other sufficient statistic. So I choose T1x to be any other sufficient statistic. Then I show that Tx is a function of T1x, and that would prove that Tx is minimal sufficient. By factorization theorem, since T1x is sufficient, f theta x can be written as psi theta T1x into hx. By factorization theorem, because if T is sufficient, you can have this factorization for some function psi theta and h. Now, what I have to show, T is a function of T1x. What does that mean? If T1x is equal to T1y, there are two sample points. T1x is T same as T1y. That should imply Tx is same as Ty. So I choose x and y such that T1x is same as T1y. And then I'll show that Tx is same as Ty. That would prove that T is a function of T1. Now T1x is equal to T1y implies that f theta x upon f theta y, because T1 is sufficient, so it is psi theta T1x into H1x, so it is psi theta T1x, H1x, psi theta T1y, Hy. But T1x is same as T1y, so they get cancelled and it is same as Hx upon Fy, H1y, which does not depend on theta. But you are given that f theta x upon f theta y is independent of theta if and only if Tx is same as Ty. So this is independent of theta implies that Tx equal to T1. So what you have proved, that T1x equal to T1y implies that Tx equal to T1, which implies that T is a function of T1. And T1 was any arbitrary sufficient statistic. So you showed that T is sufficient, and this sufficient statistic is a function of any arbitrary sufficient statistic T1. So T is minimal surface. So you have developed a method to find a minimal sufficient statistic. We just try to look at and f theta x upon f theta y is independent of theta if and only if tx equal to ty, then t is minimal sufficient. Now let's look at its corollary. Let us look at the setup of our problem. Now, if tx is minimal sufficient and t1 is a one-to-one function of tx, then t1x is also sufficient. I have given a proof, but one can develop a very small proof. First, to show that t1x is also minimal sufficient. So what it says is, if tx is minimal sufficient and t1 is one-to-one function of tx, then t1x is also minimal sufficient. Or in other words, any one-to-one function of a minimal sufficient statistic is minimal sufficient. So to show that t1 is minimal sufficient, what do you have to show? First, you have to show that t1 is sufficient. Why t1 is sufficient? Because t1 is a function of, because t is a function of t1. So sufficient statistic t is a function of t1. Why? Because t and t1 are one-to-one functions. Since t is a function of t1 and t is sufficient, then we know that t1 is also sufficient. Now, why t1 is minimal sufficient? You recall we did a result, right? This can be proved using factorization theorem, that if t is sufficient and u is a function of, and t is a function of u, so what the result which you remember, t is sufficient plus t is a function of u implies that u is sufficient. That we did, right? This proof is straightforward, just using the factorization theorem. So to show that t1 is minimal sufficient, you have to show that t1 is sufficient. That you have already proved in the first part. And then you have to show that it is a function of any other sufficient statistic. So let u be sufficient. Then since t is minimal sufficient, t is a function of u. Minimal sufficient statistic is a function of any other. But t and t1 are one-to-one functions. So t1 is a function of t, which in turn is a function of u. That means t1 is a function of u, and you have proved it. As I said, one being a function of other means, given the value of other, you can find the value of other. So what t1 is a function of t because t is a function of u. Why? Because if u is any other sufficient statistic, t is minimal sufficient, so t would be a function of u. That means given the value of u, you can find the value of t. T1 and t2 are one-to-one function. That means given the value of t, you can find the value of t. That means t1 is a function of t because they are one-to-one functions. And t is a function of u. So given the value of t, you can find the value of t1. Given the value of u, you can find the value of t. So that means given the value of u, you can find the value of t1. So that means t1 is a function of u. And you're done. That proves that t1 is minimal sufficient. So if you have a minimal sufficient statistic, then any one-to-one function of a minimal sufficient statistic is again a minimal sufficient statistic. So in that sense, minimal sufficient statistic is not unique, because you can pick up one minimal sufficient statistic, then any one-to-one function of that would be again minimal sufficient. Let us look at the second part. If tx and t1x are minimal sufficient, then tx and t1 are in one-to-one correspondence. That is also very simple. So you have to show that t is a function of t1x and t1x is a function of tx, right? In one-to-one correspondence, that is what you have to show. T is sufficient and t1 is minimal sufficient. What does that mean? t1 is a function of t. Now you can interchange the role of t and t1. T is minimal sufficient and t1 is sufficient So that means T is a function of T1. So 1 is a function of other. So they are in one-to-one correspondence. I have just given you a small proof over here. Otherwise, it is straightforward. So the first point in this remark says a minimal sufficient statistic may not be unique. That is very clear because if it exists, then any one-to-one functions of that minimal sufficient statistic would again be minimal sufficient. Now, there is a general result due to Bahadur, a famous Indian mathematician. He proved very nice, he provided a very nice example where he shows that in general, a minimum sufficient statistic may not exist. Now, constructing that example is highly non-trivial, and I don't think that would be within the scope of this course. But one can show that in general, minimum sufficient statistic may not exist. However, generally, if the sample space is a subset of Euclidean space, and the distributions are either discrete or absolutely continuous, which would generally be the case in this course, the minimal sufficient statistic will always exist. The purpose of this remark was because you may be attending various interviews and somebody may ask you, does minimal sufficient statistic always exist? Your answer should be no. So his question would be then, give me a situation where it does not exist. Now that is where you cannot provide an answer with the knowledge you'll gain in this course. Because that example, as I said, all the examples which you will consider in this course will be discrete or absolutely continuous, and your sample space would be a subset of R. So your answer, if you ask, provide me an example, you say, I don't have an example at my hand. But there is an example which is given by Bahadur. And of course, such an example is for situations where chi is different from Rn, or your involved distribution is neither discrete nor continuous. So what you should know is, in general, minimal sufficient statistic may not exist, but for all the examples which you will consider in this course, you will observe that a minimal sufficient statistic always. Now let's go to this example, x1, x2, xn, a random sample from normal mu sigma square, where both mu and sigma are unknown, so that t x equal to x bar s square is a minimal sufficient for statistic theta, where s square is this. Also, t1x is equal to x bar and t2x equal to x square are not sufficient for theta. So let me do this because let me just, so this is a normal example. Let me see the another example is theta plus 1 and x1 and xn is sufficient. Let me take these examples and then I can take a binomial example and then I can leave rest for you. Okay, so let me now share my whiteboard. So let's consider the first example. x1, x2, xn, IID, normal. Theta is between minus infinity. Sigma is greater. So first of all, I write down my f theta sigma square. X is a vector x1, x2, xn. This is a product I is equal to 1 to n, which is 1 by sigma root 2 pi or n e to power minus 1 by 2 sigma square and summation xi minus theta whole square. So that is summation xi square minus 2 theta summation xi plus n theta. That is what the x turns out to be. Now, we'll consider all the three cases separately. The first is both are unknown. Theta and sigma, both. Then I try to look at under what conditions f theta x upon f theta y is independent of theta. So I look at f theta sigma square x, f theta sigma y. There is no x over us. This will get cancelled in the numerator and denominator. E to power minus n theta square by 2 sigma square will get cancelled in the numerator and denominator. So what you are left with is e to power 1 by 2 sigma square summation yi square will come from numerator minus summation xi square. Then what is this? Plus 2 theta plus theta by sigma square. Summation xi. Under what condition this would be independent of theta? Theta and sigma square. Because theta and sigma square both are unknown. Anyone? Now note that this will always play a role, and this is independent of this because I can keep on changing. This would be independent of sigma square if and only if, let me say that eta 1, which is eta 1 I take as 1 by 2 sigma square, summation yi square minus summation xi square plus eta 2 I take as theta by sigma square, summation xi minus summation yi is independent of eta and eta 2 for every eta 1 greater than 0 because 1.2 sigma square is greater than 0, and theta upon sigma square because theta is mean. So minus infinity to infinity. This does not depend on eta 1 and eta 2. That can happen only when coefficients are 0. Right? Otherwise, they will depend on eta 1. That would happen if and only summation yi square, same as summation xi square, and summation yi is same as summation xi, which is equivalent to saying that summation xi and xi square is same as summation yi and yi square. So I can take this as tx, this as ty. T based on a sample y, t based on a sample x. And what is the function t? Its first coordinate is sum of all the observations. Second is sum of squares of the second order. Is minimal sufficient. Now, if this is minimal sufficient, then I look at T1x, which is x bar, and let us say s square is minimal sufficient. Because you know that any one-to-one function of a minimal sufficient structure is minimal sufficient. So T1 is a function of T, because given T, you can find x bar, and you can find s square, which is 1 upon n minus 1 summation xi square minus n x. And given x bar and s square, you can find summation xi and summation xi square. Because T1x is a one-to-one function of T. This solves your part 1. Now the part 2, I can look at the case. Can I erase this? Anyone? Can I erase whatever I have written on the whiteboard? Nobody is responding, right?
Yes, sir.
Okay.
Yes, sir.
Okay, great. Now let us look at a situation where case 2. Let me erase this out. Case 2. So case 2, theta is known and sigma is unknown. Now, if theta is known, then I can get rid of this quantity because then I can consume this 2 theta summation xi. No, this I cannot consume in this. I can neither consume this. So as well, I can write down this as just f theta sigma square x, because sigma is unknown, so I cannot get rid of this, I cannot get rid of this, but I can combine the two, and I can write down this as 1 by sigma 2 pi or n e to the power minus 1 square summation xi minus theta. I look at f theta sigma square x upon f theta and y. This gets cancelled, and you are left with e to the power minus 2 sigma square summation xi minus theta whole square minus summation yi minus theta. I have to show that this is independent of theta. And what is the theta over here? Only a known parameter is sigma. But this coefficient is 1 upon sigma square, so certainly this will depend on sigma square if this quantity is non-zero. This quantity non-zero, as you vary sigma, this is going to depend on the value of sigma. This is independent of sigma if and all there is. Summation xi minus theta whole square is same as summation yi minus theta whole square. Call this as tx dy. So tx equal to summation xi minus theta whole square is minimal sufficient. Now the question let me ask you is, in this case, is summation xi square sufficient? Anyone? Can anyone answer, is summation xi square sufficient in this situation? Anybody?
I guess no.
It will not be, but how will you prove this?
So Tx can't be written as a function of summation xi square.
Right, because if it was sufficient, so you prove it by contradiction. So suppose T1, which is summation xi square, is sufficient. You already showed that T is minimal sufficient. So if T1 was sufficient, T should be a function of T1. The answer is no. How do you prove it? On contrary, suppose T1 is sufficient. Then T being minimal sufficient, so let me write down MS. T would be a function of summation xi square. But T is same as summation xi square minus 2 theta summation xi plus n theta square. So to calculate summation xi minus theta whole square, you will not only need summation xi square, you'll also need summation xi. So this is not a function of summation xi square, so it is not sufficient. Similarly, in the last example, x bar and s square were minimal sufficient. Is X bar sufficient? Now you can prove that X bar is not sufficient. Why? Because if X bar was sufficient and X bar S square being minimal sufficient, X bar square should be a function of X bar. That means given X bar, I should be able to get X bar and S square. But given X bar, you can only get X bar, not S square. So the answer is no. Is X1 plus X2 and let us say X3 to Xn sufficient? X3 to Xn and comma summation Xi square. Is this sufficient? Key coordinates. X1 plus X2, X3 to Xn and summation Xi square. Is that sufficient?
Yes, sir.
It would be sufficient because X bar square is minimal sufficient, so it is a sufficient statistic. Now, given X1 plus X2, comma X3 to Xn and summation Xi square, you can get X bar square, so it would be sufficient. Is that okay? Okay. Is that clear?
Yes, sir.
Okay. Now let me move to another example. Suppose X1, X2, Xn, IID, uniform theta minus 1 to theta plus 1, where theta is between minus and beta. So what is my f theta x? Product I is equal to 1 to n. Theta plus 1 by theta minus 1, so 1 by 2, right? And then, so I can write down this as 1 by 2 to the power n, right? One by 2 to the power. This can be written as 1 by 2 to the power n. What will be the range? Each xi should be less than theta minus 1. That means maximum should be less than or equal to theta plus 1. Right? Each xi greater than or equal to theta minus 1. So that means minimum should be greater than or equal to theta minus 1. That means theta should be less than or equal to minimum plus 1. In each xi would be less than or equal to theta plus 1. So maximum should be less than or equal to theta plus 1. So that means theta should be greater than or equal to xn minus 1. This is the density. Now I look at f theta x upon f theta y. It would be 1, indicator that xn minus 1 less than or equal to theta less than or equal to 1 plus 1, indicator yn minus 1. Under what condition this would be independent of theta? Now note that if xn minus 1 is not same as yn minus 1, if the two interval are not same, you know that IAX, indicator function of a set A, would be same as indicator function of the another set when only if A is same as B, right? Because indicator is 1 if x belong to A, 0 otherwise, IX, IBX same as 1 if x belongs to B, 0 otherwise. IX is same as IBY. That means it is 1. When it is 1, it is 1. That can happen only when A is same as B. So this is independent of theta and only if the intervals are same, so that means their endpoints are same, xn minus 1 and x1 plus 1, same as yn minus 1 and y1 plus 1. I can call this as tx and this as ty. So my sufficient statistic is xn minus 1 and x1 plus 1, or then even x equal to xn, and y1 is also minimal sufficient because the two are one-to-one functions. So in this case, sorry, what dx as n minus 1 and x1, right? Because they are. So now you know how to show that a given statistic is sufficient. It's only minimal sufficient. Any doubt in whatever I explained today? So this gives you a second example. I can leave these for you. x1, x2, xn is a random sample from a population having PDF or PMF. So these are binomial. Now in this case, minimal sufficient statistic would be Tx is summation I is equal to 1 to n xi, or x1 x bar would be sufficient, and so on. This example I have already done. When sigma naught is known, summation xi minus. So in this case, what would be the minimal sufficient statistic if theta is unknown? Sigma naught is known over here. So summation xi square by sigma naught square gets consumed in hx. Minus 2 theta would come, so x bar would be sufficient. So f theta x by f theta y would be independent of theta if and only if x bar is same as y bar, or summation xi is same as y. So x bar is minimal sufficient in this case, or summation xi is also minimal sufficient. But if x bar is minimal sufficient, x bar square cannot be minimal sufficient. Why? Because if x bar square was minimal sufficient, then x bar and x bar square should be one-to-one functions. And they are not one-to-one functions, because x bar can take negative values also. So they are not one-to-one function, is minimal sufficient. And since this is not a one-to-one function of a minimal sufficient statistic, this also we did over here. If mu naught is known, the statistic which we have obtained as a minimal sufficient statistic is Sni is equal to 1 to n I minus mu naught whole square, because mu naught is known. This is minimal sufficient. But summation xi square cannot be sufficient. Why? Because if it was sufficient, then Tx should be a function of T1x. That means I should be able to get Tx from summation xi square, which is not the case. Tx is not a function of T1. And T1 is, T is minimal sufficient. Minimal sufficient statistic T is not a function of T. Now this is an interesting example, a Cauchy example. I would give this as an exercise. I may give this in the assignment problem also, that the order statistics are minimal sufficient. What you would see in this case is even the minimal sufficient statistic is of order n. It has n dimensions. So here the sufficiency does not help us much in reducing the data. Very nice example. So there are extreme situations like normal where you get sufficiency reduces to data to one dimension like x bar. Then there is another extreme like a Cauchy distribution, which says that sufficiency is not helping much. The maximum reduction you can get is only through order. Let me stop over here. If any one of you have questions, you may stay back. Those who don't have any questions, can leave. So that's all for today from my side. Any doubts anybody has? We still see 10 participants. Rahul, Sanksdeep, Shivam, any one of you have any doubts? Yes, anybody having any doubt? Okay, if there are no doubts, I still see 5 participants. It seems you people have logged on into the system but are not present for the lecture. Okay, so let me just finish the session.